The University of Dundee is at the forefront of research and discovery. Here in the Life Science building, the cell signalling team is working hard to understand the function of AMPK as a tumour suppressor.
AMP activated kinase, also known as AMPK, becomes active due to an increase in the AMP to ATP ratio within a cell. There is a need for energy, often due to the dysregulation in mitochondrial oxidation. Upon the stress response, AMPK can be phosphorylated at the threonine 172 residues of the alpha subunit by the protein liver kinase B1, or LKB1. AMPK acts to generate cellular ATP by promoting catabolic pathways and inhibiting anabolic pathways to restore metabolic homeostasis. Protein synthesis is an ATP-demanding process. Therefore, AMPK negatively regulates the action of the kinase mTOR, which has a role in protein synthesis. AMPK favors the oxidation of fatty acids and inhibits their synthesis, controlled partially by acetyl coenzyme A carboxylase isoforms ACC1 and 2. AMPK phosphorylates both to generate ATP. Finally, AMPK activates glucose uptake by the GLUT4 transporter, which will be stored as glycogen.
Can you explain the mechanisms behind how AMPK delays tumour growth?
One thing AMPK does is it tends to promote oxidative metabolism. Metabolism using mitochondria to make ATP, which is much more efficient in terms of energy. Rapidly proliferating cells, on the other hand, tend to use more glycolysis to generate their ATP. In other words, AMPK tends to promote the metabolism which is typical of a quiescent cell, a non-dividing cell, rather than the metabolism you tend to see in a proliferating cell like a tumour cell, a cancer cell.
For decades, metformin has been prescribed as a drug for the treatment of diabetes. Phenformin, however, was not considered safe due to its potential side effects of lactic acidosis, which is the build-up of lactic acid in the blood, resulting in dangerously low pH. Metformin and phenformin act similarly on the mitochondria to inhibit complex 1 of the electron transport chain, disrupting oxidative phosphorylation and halting the production of ATP. The loss of ATP is followed by an accumulation of AMPK, at which point AMPK is recruited to reinstate ATP levels, therefore resulting in glucose uptake.
Phosphatase-intensin homolog, or PTEN, is a well-established gene for tumour suppression and acts upstream of AMPK. The knockout of AMPK alpha-1 in T cells also appears to reduce tumour-free survival in mice, but the effect is not as dramatic. AMPK can stifle tumour metabolism by acting as a sort of checkpoint. AMPK inhibits mTOR as it functions in cell proliferation, and overexpression can lead to tumour growth. AMPK activates protein 53, important for the replication checkpoint G1S, where abnormal cells can be removed from the cell cycle and apoptosis can occur.
It was hypothesized that by activating AMPK, the biguanides assist in suppressing tumour growth. Surprisingly, metformin was found to have little effect on tumour suppression, likely due to a lack of OCT1 transporters in thymic cells. However, phenformin could easily enter the cell due to its lipid-soluble nature. Phenformin was shown to suppress tumour growth, however only in the presence of AMPK alpha-1.
It was therefore concluded that phenformin could act as a possible treatment for TAL. However, the side effect of lactic acidosis would still be prevalent.